Assalamu alaikum, Chem 30. So here's our fourth reaction type, which are elimination reactions. And in a sense, they're the opposite of addition reactions. So if you recall back, the addition reactions are when a double bond or a triple bond has been broken. Okay, and that can be by means of hydrolysis, halogenation, or hydrogenation. In this case, it's going to be sort of backwards of that. And what we mean is that you're going to take something that doesn't have a double or triple bond. It's going to go through a reaction, and then it will get a double or triple bond as a result. So, like our addition reactions, there are a couple of ways that this is done. So for elimination reactions, there's essentially two mechanisms that allow, you could say, a double bond be made. The first one is kind of the opposite of hydrolysis, and what it is it's a dehydration reaction, you could even say. And you'll probably hear that word more for all the bio students and chemical engineering students, in university. If you guys go into those kind of programs, dehydration reactions are kind of what elimination falls under. So we start off with an alcohol, and then here, if you notice, it says it just has an arrow, so there's no direct reactant, and then that turns into an alkene plus water. There's two things that need to be added, though. It needs a catalyst, and it needs the presence of an oxidizing agent. So your alcohol gets oxidized. Okay, so I'm going to write here alcohol gets oxidized, and it becomes an alkene plus water. The second mechanism is when you have a halogenated alkane, right? So for example, something like this, you got an alkane with a halogen on it, okay? And it's reacted with a strong base. Now, in some questions, they'll write the strong base as NaOH or KOH. Remember, just like in equilibrium, your metals are always canceled out because they end up being spectator ions. So really, the strong base is just your hydroxide ion. And what that leads to is an alkene, the halide. So whatever this was, that's now going to be a halide ion and water. Let's do a couple of examples and see how this actually plays out. So for our first example here, we have an alcohol, right? This would be propan -2-O. And so if we react this, let's say we react this with a catalyst. It could be any catalyst, that's fine. A common catalyst is usually H2SO4. Okay, but it doesn't have to be that. We'll use H2SO4, and then we'll use KMNO4, okay, for our OA. And again, you could use any of these. We're not going to test you on which one should you use, just as long as you know that a catalyst needs to be present as well as an oxidizing agent. And so what's going to happen here is, where that double bond used to be, the OH is going to be released, and the bond is going to be made over here, which will then displace a hydrogen as well. The OH and the H+, they come together to make what? Water. So when we draw our products on the other side, we end up having something like this. That's your alkene, it's your propene, plus H and OH that reacted to make water. So let's say I have an alcohol with a branch on it, right? See that little line sticking out here? That's a branch. The only thing that's really going to change after I add a catalyst and an oxidizing agent is your OH over here. So we start off with 1, 2, 3, 4. So we'll write 3-methyl butan-2-ol. And we add a catalyst and some sort of oxidizing agent here. Okay, and what we end up with, just like we did with the previous example, as that bond is made over here, this gets dislodged. There's a hydrogen that gets dislodged as well. They react to make a water. And we have a double bond here. The branch stays put because there's no reason for it to have left. And we get an alkene plus H2O as our products. And the alkene here would be 1, 2, 3, 4. It would be 3-methyl but-1-ene. Okay, let's look at another couple of examples. In this example, we have our haloalkane here, and that's reacted with a strong base, NaOH. We're going to get rid of the Na right now because it is a spectator ion, and we're just going to write OH by this. And so what we end up with here is, just like in previous examples, we're going to make the double bond where the halogen occurs at. And as a result, this is going to get dislodged, which is how it becomes Cl-. Okay? Now, what also happens is that as a double bond is made, there's a hydrogen that gets dislodged. And as you may have guessed it by now, what is going to happen to the hydrogen? Well, the H and the OH are going to come together, and they're going to make H2O. And so, once this reaction goes to completion, and of course this is under the presence of a catalyst and an oxidizing agent, okay, we end up getting something that looks like this, plus Cl- that got dislodged, plus H2O. And that fits the profile of our general formula. We said there's a halogenated alkane, or a haloalkane, plus a strong base, gives you an alkene plus a halide ion, and then water. Your alkene over here, right, 1, 2, 3, 4, 5, is pent-1-ene. This is chloride, so that's our halide ion. And then here is water. Okay? Let's look at another example. Now, sometimes when people see cyclic hydrocarbons, they panic because they feel like they're supposed to be something different, when in fact that's not the case at all. The fact that this is cyclic still makes it an alkane. So cyclic can still be alkanes. Okay, so this still falls under the same category. Now, when we name this, we start from here. So this would be 1-chloro, cyclo, 1, 2, 3, 4, 5, 6, cyclohexane, plus your hydroxide ion. And so what this is going to do is you're going to get a double bond formed over here. This gets removed and becomes Cl-. There's an H that will be dislodged. And together, those two will make water. And so when we finish this reaction over here, we end up getting, and I'll draw it in a different color. We end up getting a cyclohexene plus the chloride ion plus H2O. So the fact that it was cyclic really didn't change the reaction at all. We still see that there's an elimination reaction in the sense that a double bond is formed over here. Okay? And that concludes our elimination reactions.